to inform you. So let me introduce Dr. Shankaralingam first, and then he will introduce our speaker, Dr. Chinnaya Sami. Dr. Shankaralingam is an assistant professor, Department of Chemistry, NIT Calicut. Just before joining here, he was at EST Inspire faculty. He got a EST Inspire Faculty Award in Chemical Sciences, and also he worked as a postdoctoral research fellow in Iowa Women's University, Seoul, South Korea. And he was a senior research fellow at the Indian Institute of Technology, Madras, in 2013. He took his PhD in chemistry from Bharathidasan University, Tamil Nadu. And he got many awards and honors. So he got the Young Scientist Award in Chemistry 2019 by Venus International Foundation, Chennai. And he got the INSA DST Innovation Science Pursuit for Inspired Research, that is the Inspire Faculty Award for Chemical Sciences in 2018. He also received many international travel grants from DST and CSIR, and he presented his research work in an international conference, ASBIC-V, in Taiwan in 2010. He got many funded research projects. The main research project is the DST research project. And his main research interest is the bioinorganic chemistry, chemical biology, metal-mediated medicines, biomimetic metal-oxygen intermediates in dioxygen activation reactions, designing of new ligands and catalysts for small molecule activation and inert CH bond activation, and also to identify the short-lived intermediates, stoichiometric and catalytic reactions. So he has published many publications. He has many publications in peer-reviewed journals. So the important thing is that he has total 30 publication number 30, and more than 10 impact factor is 7. And I think recently he got a cash award for the best paper from the chemistry department. He wrote some book chapters also, and now I think two research scholars are working under him, and he completed MSc 5 PG projects. And one more important thing I can add about him is he has very good academic outreach activities. Recently, we all know that he organized an international conference on recent trends in catalysis during the February 2020. He is working in many fields. He is an active reviewer in American Chemical Society and Science Direct journals, and also he is delivering invited talks for many colleges, international universities, and international and also in international and national conferences. Sir, I invite you to chair the session. Thank you. Please.
Thank you, sir. Thank you very much for your detailed information about me. Okay, so yeah, it is my great pleasure to introduce about Dr. Swami, who is my colleague. Okay, so about Dr. Swami, so he has done his master course in general chemistry from University of Hyderabad. He completed his course in 2009, and right after his master course, so he qualified a CSIR exam and GATE, and with that qualification, he joined as a PhD student at IPC department in IISc Bangalore with Professor Tilagar to work on the main group organometallic chemistry. Okay, so then right after his PhD, again he continued as a research associate in the same lab for another 1 year, And then since 2015 till 2020 beginning, so he worked as a postdoctoral fellow at the Israel Institute of Science and Technology. So there he worked in a two different lab, so with the two different professors. So he worked in organic chemistry, supramolecular chemistry, as well as organometallic catalysis. So his research interest is organometallic catalysis and supramolecular chemistry, as well as a lot of sensing studies, and he is also interested in asymmetric catalysis. Okay, and based on his research interest and effort, so he has published 16 international papers and 8 conference abstracts, and he also delivered 4 invited talks. So with this introduction, so I would like to invite Dr. Swami to speak on his topic. What he has proposed is metal-based asymmetric catalysis. Dr. Swami, you are welcome to present your talk. You can take nearly 1 hour. Is that okay, sir?
Yeah,
okay.
Yeah, that's fine, but probably I will finish before that. That's
okay, fine. Thank you. So, yeah, okay.
Yeah,
so you can start your presentation.
Thank you, Shankar. You are very kind introduction. And good afternoon to everyone. Today I am going to talk about metal-based asymmetric catalysis. Yeah, metal-based asymmetric catalysis. Actually, my group is mainly focusing on main group organometallics and supramolecular chemistry. It's located at 213 room number in NIT Calicut. So actually, we are working on several fields of research. Mostly, we are focusing on metal-based asymmetric catalysis and stabilization of low-valent main group organometallic compounds for desired applications, and supramolecular host-guest chemistry, and photoactive nanomaterial for degradation of biological important compounds, especially drugs and other bioactive material, and sensor chemistry. So in this talk, I will mostly focus on the metal-based asymmetric catalysis. How can do design, because I'm an inorganic chemist. I will focus mostly how we can design a catalyst, and especially metal-based catalyst, how it is important, and what kind of reactions we can perform with this catalyst, chiral catalyst. So before going into the topic, I want to introduce what is the asymmetric catalysis. As you know, chemical synthesis of pure enantiomer or enantiomeric mixture, which is only one predominant without any use of resolution. So this is this process called as a asymmetric synthesis. And other words, we can say with a small amount of chiral which act as a catalyst, it will lead to formation of large amount of enantiomerically pure and enriched product. Okay, this also called as a asymmetric synthesis. As you know, US FDA in 1996, there is a 20% of chiral drugs are approved. And you can see the last year data, this one 2019, there is a 88% of chiral drugs are US FDA is approved. That indicates that what is the importance of this asymmetric catalysis. Sorry. Yeah, why we need to focus on asymmetric catalysis? As you know, the chirality plays an important role in many biological systems. In the case of DNA and glucose and amino acids, you want to make such kind of drug, we need to have a chirality. Okay, in the chirality, it will easily fit and it will cure the diseases. And many commercial drugs sold as a single enantiomer, and only one enantiomer is very active curing the disease. And other enantiomer, it can be silent or it can lead the other activity. I'm showing here some of the drugs and the activity, and due to this, we need to purify. You need to synthesize the selectively only one isomer, which is the active in the medicinal chemistry. So how we can achieve the asymmetric synthesis? So there are several synthesis methods. I will show here a couple of them. One is the chiral pool synthesis. We can synthesize. Yeah, we can synthesize this kind of ligand, chiral ligand, and these ligand we can attach to any metal. Then that metal will act as a very good asymmetric transformations. And another one, chiral auxiliaries. As you know, these chiral auxiliaries, it can attach the reactants. Then it will form a selective, like single isomer of product. After formation of product, we can remove easily this chiral auxiliaries. And another one is the asymmetric catalysis. And what are most used chiral catalyst? So there are three types of asymmetric catalysis are there. One is a metal ligand complexes. Another one is a chiral organocatalyst and biocatalyst. So in this talk, I will focus mostly on metal ligand complexes. What ligands we can use for asymmetric catalysis. Especially in this talk, I will mostly focus on asymmetric hydrogenation reactions. Okay, this is a pictorial representation of metal-based chiral catalyst. As metal will form a 5-membered heterocyclic. You can see here, this is a 5-membered heterocyclic, and it contains the rigid backbone, and it have a center of chirality. Like this oxazoline have a chirality. It is a center of chirality, and this one is stabilized by any bulkier anion like a hexafluorophosphate or BARF. Okay, these kind of anions it can stabilize by especially the rhodium or iridium. So in 2001, 3 legendary got a Nobel Prize because of asymmetric catalysis. Is the Williams, Naiori, and Sharpless. In the Williams, he choose a chiral rhodium complexes for hydrogenation of this compound and end up with L-DOPA. Is the synthesis of this L-DOPA. L-DOPA is proved the useful treatment of Parkinson's disease. And in the case of Naiori used the ruthenium complex, this ruthenium chiral catalyst. He used the hydrogenation of this compound, you end up with this, and this compound is used as an anti-inflammatory agent. In the case of Sharpless used titanium tautorite based chiral catalyst for selective epoxidation, asymmetric epoxidation reaction. Due to their legendary work, and they awarded as a Nobel Prize in 2001. So I will show some of the chiral catalysts which are extensively used in past few decades. These are the phosphine and oxazoline based chiral catalyst. We can change the R group with the toluene, cyclohexane, and as well as a phenyl. And here also the N-phosphoryl, this ligand also we can change the substitution on the phosphorus, and this kind of ligands are well known in the literature, and they used the several asymmetric transformations like asymmetric hydrogenation, asymmetric hydrosilylation, asymmetric borylation, and several kind of reactions. And furthermore, I am showing here is the phosphonate and oxazoline ligands. In the researchers are focused on this kind of system which is easily coordinated with metal, and it will act as a very good catalyst, and they're easily substituted R with phenyl and toluene, toluene, and these are here they can change the R is isopropyl tertiary. And here also they can easily synthesize the several asymmetric ligands for asymmetric transformation reactions. So as you know, several decades there is a lot of work on the phosphine based ligand, but in here I will show how the NHC also will fill the ability of phosphine. Here I am showing the pictorial representation of N-heterocyclic carbene. These are the N-heterocyclic carbenes, and these complexes have a carbene ligands have a more thermostable as compared with the phosphine. And also these N-heterocyclic carbene metal complexes are more highly thermally as well as air and moisture sensitive. In the case of phosphine ligands, phosphine will be oxidized, and it will be not that much stable in the presence of oxygen. and moisture. This is the one of the example of oxazolene and NHC ligand. And these are the some of the few differences between the PASPine and NHC ligand. As you know, PASPine and NHC ligands are strong electron sigma donor, and due to this, the electron density of metal center have much higher. And as I told, the NHC is donates more strongly, and on the other hand, it will accept very poorly. Due to this, the NHC metal complexes generally have a greater electron density at the metal center as compared with PASPine. And the Tolman cone angle, as you know, in the case of PASPine ternary complexes, is suitable for cone angle. In the case of NHC compounds, these NHC compounds are in the two-dimensional, and planar ligand is the NHC. This cone angle is not applicable here. So I will start my work. The first part of work is asymmetric hydrosilylation of estophenone by rhodium NHC chiral catalyst. Before entering into the work, I would like to give a brief introduction. Here we choose a pyridyl NHC NHC ligand. So here I would like to show how many pyridyl NHC ligands are known. Here very few pyridyl and NHC ligands are known in literature as the chiral and non-chiral. And further, recently, Gowda and co-workers synthesized this kind of NHC and oxazolene metal complexes according to this procedure, and they structurally characterized, and they use the catalytical activity towards the estophenone using the hydrosilylation reaction. Here, complex 3, which is the AR is the mesitylene group. Here is the complex 3 shows the much better enantiomeric excess as well as a good yield. And for this is at room temperature. Further, they move to minus 60, and dichloromethane as a solvent, and they end up with a very good enantiomeric excess as well as a very good yield in an aromatic system. And further, they focused on the aliphatic ketones also. We can see they end up with a very good enantiomeric excess as well as a good, very good yields. So we keep these things in mind. We can this paper showed very few substrate scope. We keep these things in mind. We design a molecule which can use the wide variety of substances and with very good enantiomeric excess as well as a good yield. According to that, we synthesized a rhodium NHC chiral catalyst. According to this procedure, first we taken a pyridyl cyanopyridyl aldehyde reacting with amine. Amine end up with imine, and we are reacting with chloromethyl ether, and we can end up with this kind of NHC. And then this NHC we microwave in the presence of zinc acetate with chiral amino alcohols, and we end up with chiral oxazolene and NHC compound. And furthermore, we treated with edge and silver oxide and rhodium chloride. We ended up with our final catalyst. And this catalyst is structurally characterized by NMR as well as HRMS. Unfortunately, we didn't get a crystal structure of this catalyst. So this is the NMR of one of the molecule. This molecule shows all oxazolene as aromatic as well as called protons as a different in environment. We can see here clearly. All are showing different environment due to these one have a C1 symmetry. It is in a chiral in nature. So further, these complexes are confirmed by HRMS. This is the HRMS spectra, and we successfully synthesized a series of catalysts and structurally characterized. After getting a pure compound in hand, we further focused on the optimization of reaction conditions for hydrosilylation reaction. So here we taken a 6 catalyst, and dichloromethane is the loading is only 1 mole %, and this is additive. Only with no additive, the 5E, this compound shows the better enantiomeric excess as well as a enantiomeric excess as well as a yield. When we are using the AgBF4 as an additive, we can improve the yield as well as the enantiomeric excess. Furthermore, we focused on the temperature. We carried out the reaction at -20, 0, as well as +20 and 40. These catalysts are much active at +40 degree, and the yields, and this is the yield as this is the enantiomeric excess. Furthermore, tune the silane group, and we use the ternary silanes as well as a naphthyl silane. So here we are using the ternary silanes. We end up with zero reactivity. There is no formation of product. And in the case of naphthyl silane, we end up with a very good yield as well as a enantiomeric excess, which is comparable with the diphenyl silane. And furthermore, we move to decrease the catalyst loading. Here we choose a two things. One is a 0.1 mole %, another one is 0.01 mole %. So in the case of 0.1 mole %, we end up with a very good yield as well as an enantiomeric excess. Whereas in the case of 0.01 mole %, we are comparable with the enantiomeric excess, but the yield is very less. So this is a possible mechanism for this reaction. First, actually, rhodium catalyst, the oxidative addition will occur. It will add like this oxidative addition, and alpha hydrate will transfer, and after successfully transferring alpha hydrate, and this carbonyl will coordinate on silicon. After that, hydrate will transfer from the rhodium to carbonyl unit. So we'll end up with this compound. After successfully reductive elimination, we'll get our desired product. So as I discussed, actually this project we designed for this catalyst activity for wide variety of substrate. Here we chosen the several substitution, and the phenyl is the meta position as para position, and the meta as well as ortho position. And also this catalyst have very good functional group tolerance. And one is here we choose an amine, nitro, cyano as well as a ester. So here we can see clearly these all compounds have a better enantiomeric excess as compared to known literature reports. And also this compound we applied for naphthalene compounds. Also naphthalene also shows better enantiomeric excess as well as a good yield. And furthermore, we focused our attention to alkyl ketone substitution. Here we chosen a several alkyl substitution, and we found out that these alkyl substitutions, the enantiomeric excess is quite decreases, and the yields are more or less as compared with the aromatic unit. And further, moreover, we chosen the heterocyclic keto substance, and here we chosen the thiophene and pyridyl compounds, and these compounds also found to be very good enantiomeric excess as well as a moderately good yield. Okay, after this, further we checked our catalyst activity in the natural products. We chosen here the estrone, thiazole, and carbon. We chosen and we reacted. We followed the same procedure, and we end up with a very good diastereoselectivity. These compounds are going. This reaction going to only one direction, and it is forming only one diastereomer. So that is the story of first part, and I will conclude end of this talk. What is the first part conclusion? And the next part is the asymmetric direct hydrogenation of estophenone by iridium NHC complex. So here we change the metal rhodium to iridium, and as you know, iridium complexes are very good direct hydrogenation reaction. before entering into my talk, I will give you some introduction. What kind of iridium complexes are known? So and here I will show in NHC and other metal complexes, and which found to be direct hydrogenation reaction. And these compound, they used the 25 bar hydrogen, and still they end up with 0 enantiomeric excess. And they change the substitution on ruthenium, and they end up with some enantiomeric excess. And I will show very detail how much enantiomeric excess they got. And they synthesize the metal complex according to this procedure, and they synthesize them. They structurally characterized. They got a single crystal X-ray, single crystals also. And these are the data they got about the enantiomeric excess. They used a very high pressure. And as you know, using the hydrogen is very dangerous. If it is very high pressure, it can blast. It is nothing but a bomb. So here they used the 25 bar hydrogen gas, and they got very less enantiomeric excess value. You can see clearly this the 35 is a 4-chloroacetophenone got a very best enantiomeric excess that is a 35, and others are racemic mixture are very low in the enantiomeric excess. So furthermore, in the same group, they synthesized this kind of ligand, this kind of helium-based ligand, and they used it for direct hydrogenation. Here also they used 25 bar and 50 degree temperature, and we can see here they showed here as the ratio. So we can see all are close to racemic in nature. So we can see clearly, this means actually these catalysts are giving more racemic product. It is not giving any enantiomeric excess. So we keep these things in mind, and we synthesized this kind of metal complex, and as I discussed in the previous part, we synthesized this metal complex in iridium complex, and after successfully synthesized this, we characterized by NMR as well as HRMS. Unfortunately, in this series also we didn't get the crystal structure, and furthermore we move to our catalytic activity optimization reaction. Here we consider two things. One is the different solvent as well as a different temperature. As I'm showing here, compound 5C, and here methanol, THF, dichloromethane, estronitrile, and toluene, we use different solvents. And here we can see the yield is very excellent, is greater than 99%, whereas enantiomeric excess is only the 5C found to be better. And 5C found to be better, and in toluene solvent, and further we did other catalyst also in the toluene, and we can see other catalysts also showed very less enantiomeric excess. And what we did, we decreased the temperature from room temperature to 0 and -20. Okay, here what happened in the catalyst 5A, this one is found to be very good enantiomeric excess as well as a very good yield, and others also found to be more or less similar kind of results except B. And this compound, and furthermore, we here increase the enantiomeric excess because from the room temperature to 0 degree. Further, we can expect a better enantiomeric excess. Due to that, we increase the temperature -20. And this here all compounds are found to be more or less same enantiomeric excess except B. And these compounds, we are going to down the temperature also, enantiomeric excess, we are unable to increase the enantiomeric excess. So this we consider the catalyst is very active at 0 degree toluene, and at hydrogen is 6 bar. Actually, here I would like to mention we use the very less pressure. As we know, previous literature reports, as I showed, they used a 25 bar, but here we decreased almost 4 times less. lesser than that. Still, our catalyst is very active and it's found to be very good enantiomeric excess as well as a very good yield. After successfully understanding this optimization reaction, we move to substrate scope. Here we choose a different substrate scope as a para, meta as well as a ortho substitution. And here we can find these compounds are found to be very, very good enantiomeric excess. You can see clearly. As compared to literature, as I showed previously, ruthenium and iridium complex, they found to be highest is 35% enantiomeric excess. But here we are able to get almost 90 and 80, 85 or 76 and this kind of very good enantiomeric excess. And the yields are all reactions are very completely conversion, and we no need to bother, just we can filter through the silica, then we can check enantiomeric excess. Because we are using the hydrogen, there is no byproducts. We need to remove the only catalyst. So after that we check the isolabeling experiment. Because we need to find out it is really direct hydrogenation or transfer hydrogenation. So here instead of hydrogen we used the deuterium. So after using the deuterium we found out the deuterium percentage here is almost 97%. This is a comparison NMR of this proton NMR of these two compounds, and this is a proton hydrogen NMR peak here, but here there is no hydrogen. This is the deuterium. We can see clearly it is in oxygen. And also we can able to observe some amount of this CH2D also here. We can see this is CH3 and this CH2D. And this reaction is going through, some amount of reaction is going through is the enolate mechanism. Due to that reason, we are able to get CH2D also, some little amount. I think the 10% or less than 10%. So furthermore, we applied this one for sulfonamide. As we know, sulfonamides have a very good medicinal property. Here I'm showing the some of the sulfonamide which are the very, very useful drugs, and these are the non-chiral and these are the chiral. So we focused on our thing to synthesize the chiral sulfonamides. So this is the dynamic kinetic resolution of alpha substrate ketone. What we did here, we taken a ketone which is the chiral, and we subjected to under same condition using the hydrogen, and we end up with a very, very high diastereomeric excess. So we can see here it is the diastereomeric ratio is 95:5, and this is also 95:5, and this is a 94:6, and this is a 91:9. So this reaction, even though we are taking a racemic mixture, but still we are getting a better diastereomeric ratio. And in the case of these compounds are found to be very less diastereomeric ratio because of the flexibility of this compound, and this is a racemic in nature. And this also we got very less, and 2:1 ratio. And this is the stabilizing due to this aromatic ring, and it is stabilizing the unolate form. Due to that, we are getting a 2:1 ratio of diastereomeric ratio. And furthermore, as I discussed, and we synthesized several sulfonamides, and we taken a similar kind of substrate, and the sulfonamide we got a very, very good to excellent diastereomeric ratio. And the yields are all compound yields are very, very good and excellent. So I would like to conclude my talk. As I told Shankar, I will finish quickly. I finished almost. I would like to conclude my talk in this way. As I showed first part of my talk, we synthesized the rhodium-1 chiral catalyst, and these complexes are very highly active for enantiomeric hydrosilylation reaction of a wide variety of substituted ketones. Even we check the aromatic heterocyclates also, it is very good for hydrosilylation reaction. And these compounds are typically is the greater than 90% yields, and also enantiomeric excess are ranging from 80 to 95%. And the second part of my talk, we demonstrated the asymmetric direct hydrogenation reaction of ketones that produce a very good enantiomeric excess as well as an excellent yield up to 93% of enantiomeric excess. And isotope labeling studies shows that both direct asymmetric hydrogenation and dynamic kinetic resolution is confirmed that is a preferable direct asymmetric hydrogenation over the transfer hydrogenation pathway. And thank you very much for your kind attention. I'm very happy to answer you if you have any concern or doubts.
Thank you, Dr. Swami, for energetic lecture, for your energetic lecture. So now it is open for audience. So participants, you may ask questions if you have any doubts or inquiries. You can ask him. He will be very happy to answer for your queries.
Yes.
Dr. Swami, it was
Yes,
it was a very good, very informative, very pleasant, very dynamic lecture.
Thank you, sir.
All appreciation. Great.
Thank you, sir.
This in the first set of reactions.
Yes, sir.
Hydrosilylation of ketones.
Yes, sir.
You said that AGBF4 is being added as an additive to improve the performance.
Yes, sir.
Yeah. So how does AGBF4 contribute to that?
Sir, actually this have a rhodium chloride complex.
Yeah.
Okay. We want to remove the chloride to make a rhodium cation. Okay. Once the rhodium cation, that will be the active species in the reaction.
Right.
So due to that reason, we added the silver tetrafluoroborate.
Now, how does it act? What is its specific action?
Sir, actually, the silver tetrafluoroborate will pick up the chloride.
Oh.
That rhodium will become a rhodium cation, and the anion is the borate. So the cationic species of rhodium, it is very active. Then whenever you are adding this diphenylsilane, it will undergo the oxidative addition. Then further reaction will continue as I showed the proposed mechanism.
Okay. Similarly, in the second set of reactions, you have found the 6 varieties of catalysts. No, 6 varieties of catalysts: A, B, C, D. E,
this one, sir.
Hydrogenation reactions. No?
Yeah, hydrogenation, actually we synthesized only 4 catalysts.
4 catalysts. So,
yes,
in what sense? You have different substituents.
Yes, sir.
So how do they contribute to the difference in efficiency?
Sir, actually we focused on the steric hindrance section. First of all, this reaction, we are introducing the oxazolene. This oxazolene position, it will direct the attacking of the substrate. Okay, and also this whatever bulkier group, this isopropyl and this one, it will protect from other side of attack. And actually the similar reports are there in PASPIN. Actually the PASPIN and this NHC have a little difference. The PASPIN have a 3-dimensional in nature, the NHC has a 2-dimensional. 2-dimensional in the planar in nature, either incoming group attack either backside or front side. Due to that reason, we are unable to control the enantiomeric excess actually. Still we are losing some of the enantiomeric excess due to the planarity of the NHC.
Great, thank you, Dr. Swami. Thank you.
Thank you, sir. Yeah.
So, thank you, so Swami. Dr. Swami, there is a question from students in the chat box.
Yeah. I will see 1 minute. Yeah. Which step do you think the stereoselective?
In slide number 23.
Okay, okay. I will tell you. Just let's go to slide. See, actually, after attacking, after oxidative addition, this when it is attacking the transferring the hydrate is the rate determining step here. Okay, hydrate transferring is a which side is the hydrate is transferring, either front side or back side. It will determine the step. Okay, are you understood? You clear?
I think they are not able to unmute, no, because the question is from Shara. So, Shara,
Yeah.
Sir, I can't see the slide.
Oh,
Swami,
okay.
you can, yeah,
I will share the slide. I will.
yes.
Yeah. See here. Actually, after if this ketone will come and attack on silicon, then hydrate need to be transferred. Right. This step, hydrate need to be transferred either front side or back side. This will be the determine the stereoselectivity of the compound.
Okay, so
May
there are
I
other-
extend that question?
Okay, sir, okay.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So in your this first case,
Yeah.
ketone hydroxylation.
Yes, sir.
So you have used asymmetric catalyst,
Yes, sir.
correct?
Yes, sir.
Then you have done hydroxylation reaction,
Yes, sir.
and most of the case you got more than 80% enantiomeric excess.
Yes, sir.
So just like what Sehara asked,
Yeah.
how do you explain that? Why we are getting one enantiomer more than other? Right? If you change the asymmetric center of the catalyst,
Yes, we'll get a different enantiomer. Actually, whatever I showed we got a yes isomer. Yes isomer. Okay, we synthesize the actually our catalyst also yes isomer. We choose a amino alcohol is a yes conformer of yes amino alcohol, and we end up with the catalyst is a yes, and we synthesize the R also. We got a exactly different isomer.
okay, you got both.
Yes.
Yeah. Okay.
Yes, we got both.
Okay.
Hello, sir.
Yes.
Sir, I am Amala.
Yes.
I have a question.
Yeah.
Sir, how can we calculate this enantiomeric excess?
Yeah, myself, I use the HPLC. Actually, we need to use the chiral HPLC, and we need to inject the racemic mixture. And after injecting racemic mixture, and after the reaction finished, we can purify the compound. Then we'll inject, and we can calculate the ratio of two peaks. How much it is? It is like a 1:1 or 90:10 or 80:20 like that. We can calculate. That is easy. Yeah.
Okay, thank you, sir.
Yeah, no problem.
Okay, so there are some other questions in the chat box.
Okay, Shankar, can you read it? Better?
I'm going to read it. Yes.
Okay. Yeah.
So the question is from Manivarna Nair.
Yes.
So thank you for such an enlightening seminar, sir. My question: what methods are used to propose the final structure of the catalyst generator?
What method?
What methods are used to propose the final structures of the catalyst generator? I think that is NMR and mass.
Yes. Yeah, already I discussed. Actually, we check the NMR, mass as well as a CHN analysis. Okay, we confirm the catalyst in that is the way, and also we in the case of silver tetrafluoroborate, after addition of silver tetrafluoroborate also we confirm the active species of the rhodium catalyst. Okay, when the before addition of silver tetrafluoroborate and after addition of silver tetrafluoroborate, we monitor the NMR, and we check the NMR peak shifting.
Okay, fine.
Yeah, and we confirm. Yes.
I think what I am going to do is that the students can unmute by themselves, and then they can ask the questions directly to you. So
Yeah, that's fine.
suggestions, so they can ask directly. So
Yeah.
before that, based on your answer, so I have
Yes.
a supplementary question. Okay.
Yes.
And
Yeah.
it is in relation to Dr. Professor Vanikesan sir's question.
Yeah.
So why specifically you have chosen silver BF4? Why not silver perchlorate or why not silver triplet?
No, Shankar. Actually, we chosen several silver salt actually, and we chosen silver triflate and silver hexafluorophosphate and silver tetrafluoroborate. But this reaction give better enantiomeric excess as well as a better yield in silver tetrafluoroborate. And also in the following one paper 2009 in Chemistry European, as I showed the anglichem followed by that paper, and they discussed the anion effect of anion is very much. Okay, when they are using the bulkier anion or smaller anion, the enantiomeric excess will be drastically dropped. If the silver tetrafluoroborate only the exactly anion to accommodate and it is proceeding the reaction, then it is giving the very good enantiomeric excess. And they calculated theory and those things. Actually, I'm sorry to answer. I don't know exactly how they calculated and why only the silver means tetrafluoroborate anion only influencing this. And they calculated whatever I told, that is a very little. And the theory, they did lot of theory. I'm sorry, Shankar. I don't know. Yeah.
Okay, fine,
Yeah.
no problem. So there is another question from Vidya CV, PhD student. So Vidya, can you unmute your mic by yourself and ask the question? If you can't, Sid sir, can you unmute Vidya CV?
Okay, I will try, sir.
Yes. So Vidya, can you try by yourself, because Sarah could unmute by herself.
Yes, now Vidya is already, now it is unmuted.
Yeah.
Yes. Yes.
Yeah, Vidya, so you are already unmuted. So please, you can ask the question.
Hello, sir.
Yes. Can you increase the sound, please? Actually, we cannot hear.
Hello, sir. Now, can you hear me?
No, still you can increase. That is good. Sorry. Yeah, you can speak little louder. Then everybody can hear also.
Hello, sir.
Yeah.
Now I think I'm audible.
Yeah. Tell me.
Sir, you have said the substitution in the rings will increase the EEN.
Yes.
Thing. If other than alkyl group, is there any other substituent we can add to increase the EE? And another question is there any role effect of the metal in the EE? Can we substitute rhodium with other metal to increase the EE?
Yeah, actually, the second question, first I will answer the second question. Actually, in I work with Professor Graham de Ruyter in Technion, and he's now working on iron cobalt metals. But I'm not sure how the enantiomeric excess is influencing the changing the metal. But I think it can be, but that depends on the what kind of metal you're choosing. You are choosing the different metal, it will be different properties, or either it can increase the enantiomeric excess or it will decrease, or it won't be the reactivity also.
Okay.
Yeah. And the first question, actually, I didn't understand. Can you repeat one more time, please?
You have used different alkyl substitutes in the ring.
Yes.
For different catalyst. Can we use any other substituents instead of this alkyl?
So, Dr. Swami, so you have used in the substrate scope, so you have used a variety of substrates.
Yes.
And I think you have mentioned that alkyl group will show better EE, and her question is that any other substitutions other than alkyl, so which will increase the EE or not? Is that okay? Is that correct, Vidya?
Yes, sir. Yes.
Yeah.
Where the alkyl? Oh, you're talking this slide? This slide you're talking without, yeah? Shankar, really, I didn't understand your question actually. Sorry. Means actually instead of acetophenone, need to use some other substrate like that.
No, I mean, what she has
Swami,
mentioned.
Swami,
Sir
can,
asked a question.
Yes.
Yeah, Vidya, please. Yes, go ahead. Vidya?
Yes. Vidya.
Okay, fine. So she has some issues with
Okay,
Swami,
that
probably
system.
I can extend that question.
Yeah.
You have taken several substituents,
Yes,
several
sir.
substrate,
Yes, sir.
but varying different substituents. Right?
Yes, sir. Yes, sir.
Is there any correlation between the
No, sir.
substituents with enantiomeric excess?
No, sir. No. Actually, I can clearly show here. I'm introducing methyl at tertiary butyl. It is coming more or less same. And methoxy also more or less same. Fluoro, chloro also it's coming more or less same. Actually, here the substitution is not influencing actually the enantiomeric excess.
Okay, that means steric or electronic effect of the substituent doesn't have any role.
Yes, exactly, sir. Exactly.
Okay. So
Yeah.
one more question. You have
Yeah,
talked
tell me.
about the isotope labeling and say that transfer
Yes, sir.
hydrogenation. Can you
Yes, sir.
explain a little more on that? That's right.
Sir, I actually there is a hydrogenation reaction.
Yeah.
Sometime actually they will use as a transfer hydrogenation reaction. Like they can use a base and isopropanol. When you're using base and isopropanol, this hydrogen will generate and that will be in the reaction that will perform and that will cleave in the presence of metal and the reaction will go. Okay, that transfer hydrogenation reactions are well known. Okay, actually I want to rule out that really my catalyst is doing transfer hydrogenation or hydrogenation, direct hydrogenation. To that, what we did, if it is transfer hydrogenation, even though we are using the deuterium, here we can see that deuterium 97%, it should be the protonated. Because actually there the transfer hydrogenation we are no need to give the hydrogen. Already in situ is generating from alcohol. To avoid that, to eliminate that thing, and we use the deuterium and we end up with 97% of deuterated product. That means it is direct hydrogenation. This is not a transfer hydrogenation.
If that's so, then why there is no deuterium on oxygen atom?
Sir, actually this reaction actually this reaction will go through unolate transformation and I'm not sure, sir. Actually, this one we didn't trace this oxygen means OH group. Actually, I don't know. It is deuterium. I don't think so. It is deuterium. Maybe that I'm not sure, sir. It is deuterium or not. I'm sorry to say. It is very thanks for your information, but I don't know. I'm not sure. It is deuterated or OH or DO OD or OH. I'm not sure, sir. Actually, we didn't focus on that. We focused on only this deuterium atom.
Okay.
Yeah, I'm sorry, sir. If I will get back to you if once I will go through very properly. If actually we did several experiments, I will go back. I will go back and I will get back to you. So
Have you done any kinetic study other than this?
No, sir. No, we didn't do. Actually, our target is to make a catalyst. Actually, we want to do some kind of like actually we plan to do the kinetics with iron and manganese and cobalt metals. But this iridium and rhodium metal catalysis is well established. Actually, I got a job here. I came here. I didn't do that. Maybe I was there in postdoc. Maybe I should have done that also. Yeah.
Okay, Dr. Chinaya, can I ask some queries?
Yeah. Go ahead.
Yeah. So I just want to know, you were trying to do some asymmetric hydrogenation on acetophenones, right?
Yes.
Para-substitute acetophenones, right?
Yes.
Yeah. So have you done with any nitro substituent on the para position?
Hydrogenation?
asymmetric hydrogenation of
Yes, yes.
is nitro substituted acetophenols. Have you tried
Yes,
it?
yes, we did, but the reaction is failed actually. The reaction is not going.
Oh, why? Why?
There is a problem with nitro group. Actually, we are using the toluene, and we are using the another additive is a potassium tertiary butoxide. And these toluene and the nitro groups actually once it is forming the enolate group, and this is forming like a gel kind of thing. The solubility have a problem. Due to this solubility, we didn't observe any the product.
Uh-huh.
Yeah, which one?
Which mechanism you are anticipating for this conversion?
This like a no. Actually, we need to speak about first part or second.
The
part.
hydrogenation. I mean, this thing.
Yeah, hydrogenation reaction. Actually, first what will happen? This hydrogen will be hydrolytically cleaved, and we confirm that one also. Once actually hydrogen is hydrolytically cleaved. After that, once the acetophenone attacking the this mechanism is well known. That's why I didn't keep. Anyway, I will explain. And this acetophenone will coordinate with iridium. Then a hydrate will
No,
transfer.
I'm asking about the enolate formation or the direct hydrogen. Yeah.
Direct hydrogenation.
Okay.
You know, already I have explained here. There is a some percentage of enolate also is there. Enolate formation also is there, but that is a very less than 10%. That's why actually we are able to get a deuterium here, CH2D.
But is it same for all the compounds? That's it.
Yes.
Yeah.
Yes. Yes, it is same for everything.
Okay, you have evidence for that.
Yes.
Okay, so but like if you compare with you did this as an extension of the silylation, the first part that you have shown, okay, but it doesn't match, right? The enantiomeric excess is widely different in this case, right? But in the silylation case, enantiomeric excess was very good, but here it is not so, right?
Yeah, madam, actually before coming this talk, I have showed what are the literature reports shows actually. This is a direct hydrogenation. This shows the highest as enantiomeric excess is only 35. Here is almost this compound is almost around 10. So compared to these literature reports, my compound shows such a great property, such a great enantiomeric excess. Okay, unless we need to compare the literature review, literature data. This is my opinion. I feel.
Yeah. But definitely other compounds also will be there, no?
Exactly. That one only. Actually, my target is the only synthesis of catalyst. Okay, this is one of the reaction I did because I am an inorganic chemist. Yeah, inorganic chemist, I will focus only the catalyst, how I can design and those things. Organic people can do this kind of thing, but unfortunately, I did this one also.
What I meant is not that. Actually, what I meant is for the same catalyst, you are getting a big difference in the enantiomeric excess.
Not same. There is a iridium, this is a rhodium, right? There is a huge difference between the iridium and rhodium.
No, I'm talking about the hydrogenation only. Just like you have mentioned, you have for the same like changing the para substituents. You cannot it didn't work for the nitro and cyanide.
Yes, exactly.
So the enantiomeric excess is very poor there, right? Okay.
Yeah, no, that reaction not at all work actually. If reaction is not at all work, actually we no need to speak about enantiomeric excess, right?
But you cannot.
First, we need to get a product, right? After getting a product, only we can understand it is really how much enantiomeric excess is coming. I am talking if the reaction is not going, how we can expect the enantiomeric excess?
No, not like that. Like you cannot say that it is applicable to para substituted acetophenols, but you can say that for some like selected some specific compounds.
Yes, madam. Yes, exactly. I agree with you. Actually, this catalyst is not suitable for nitro, cyanide, other substitution.
That's what I meant.
Yes, exactly. I agree with you. These are not suitable for those things. Yes.
Yes, yes, that's right.
Yeah.
Okay, okay, thank you.
Yeah.
Chinmay.
Thanks, madam. Yeah. Thanks, madam. Thank you. Thank you. Yeah. Yeah.
Thank you. Any other questions from the participants? Other
Hello.
faculties and PhD scholars? Yes, yes, please. Yes.
Sir, can I ask something?
Yes,
Yes. Yes. Yes.
yes.
Go ahead,
Yeah.
please. Yeah.
Sir, what exactly does the cone angle do in this case? Because in NHC,
No,
if it's
no.
planar,
I told it here. Cone angle is useless.
okay, so then why do we get an enantiomeric axis when we have a planar NHC, and so it can attack from both the sides, right?
No, actually, I have introduced the chiral system. Okay, I have introduced the chiral system as well as the bulky groups. Then this chiral system, it can direct only one direction. Only it will attack only one either front side or back side. It won't allow due to this chirality. It won't allow both sides. If I'm making this racemic mixture, plus and minus or R and S, so whatever, so I'm using the chiral compound and I know the chirality of the product. You got it? Answer?
Yeah, okay.
Yeah, okay.
So, any other questions from the students or any other faculties? Okay, so
Yes.
Dr. Chinnay, I have a small question. Of course,
Okay.
it may be continuation with other faculties and the students.
Okay. Okay.
In your
Okay.
experiment, in your first part of your experiment,
Yes.
did you gone through any substitutions instead of a simple acetophenone in place of a methyl? Did you gone through substitutions like phenyl or heterocyclic points,
Yes.
those kind of things?
Yeah, actually, what happened? We checked the ethyl and tertiary butyl. There, actually, the reaction is not completely going. Like only we are getting a 20 or 30%, and enantiomeric excess also not that much good. Actually, there is a substitution there influencing the enantiomeric excess.
Okay, so in your first part, in the case of acetophenone, you are having so many substitutions that electronically is not affecting, but you are telling that the other portion where in case of methyl, that is affecting your reaction, right?
Yes.
Is that correct?
Yes.
Okay, so since you concentrated on enantiomeric excess, you haven't performed any other experiment.
No, I didn't.
So like benzophenone, did you perform with a benzophenone?
Yes, actually we performed benzophenone, but that is the achiral benzophenone.
Yes, of course.
Yes,
I mean, I am talking about.
We performed, the reaction went well. But actually, after that, we did use other substitution.
Mm-hmm.
Actually, we focused only on the acetophenone, mostly 90%. Not 90, maybe 99% we used only acetophenone.
Understand. And from the previous question, the answer you suggested.
Yeah.
So since in your catalyst, it is the chirality is there, so it is directing the hydrogenation from a particularly one side.
Yes.
So that's the reason you are getting enantiomer is more in nature, right? That was your answer.
Yes.
Okay. Yeah. Thank you, Chinaya.
Yeah, no problem. Yeah.
Hello.
Yes.
Sir, the lecture was so informative. And in one of your introductory slides, you have mentioned, you said something about Parkinson's disease. So is that a metal-based chiral drug?
No. That is the compound actually. L-DOPA. This is called L-DOPA. Actually, is the Williams, Professor Williams is synthesized. This is the L-DOPA. It is proved the treatment in the Parkinson's disease. Yes, this is not a metal. Yeah.
Okay. So my doubt is, it is not related to synthesis. My doubt is how the chiral resolution of a particular compound influences their biological properties. Do you have any kind of idea about this?
Actually,
there are
yes. Actually, I am means biology. I am not a very good in biology because I'm in inorganic chemist. Anyway, I will answer.
So have you ever come across
Yes,
like that?
yes, some extent I will answer, but I don't know if my answer is correct or not. See, actually, I think you know about lock and key, right?
Yes.
Lock and key rules.
Sir.
Actually, once you have a pocket, is the engine or anything pocket, and only one isomer have it will fit with the key lock. Sorry, this the engine is the lock and this the compound is the key. So it will fit. Actually, you are changing the configuration or to yes. It cannot fit actually. It cannot fit means obviously it will be inactive.
Okay.
Yeah.
Okay, so do they switch between their R and S isomers when
Yes.
applied to biology?
Yes. Yes.
Okay.
Yes.
Okay, sir. Thank you.
No problem.
Sir, I think in a chat box, one more question from Rarima R.
Yeah.
Rarima, can you speak now?
Yeah. Can you speak directly? No problem. I believe. I think.
I think it is more or less same as the question what Monisha has asked actually. So,
Okay.
so how does the stereochemistry influence the therapeutic action?
Oh, okay. Same. Right. Yeah. That's fine.
It is
I
same.
believe. Yeah.
Okay.
Yeah. I think she understood. I believe.
Yeah.
Okay.
So any other questions from any other participants? Okay, Dr. Swami. So I have
Yes.
I have two more questions. Okay.
Yes.
So in your catalytic cycle, so where you have proposed a mechanism in slide number
Yes.
23. Okay. So do you have any evidences for that intermediates? Do you have any evidence for the rhodium hydride formation?
Yes. Actually, I'm sorry to say, Shankar. Actually, this one we order the deuterated diphenyl silane, but unfortunately we didn't get. Actually, same question asked by reviewer when we submitted this paper to Organometallics, and it published also already. Actually, they asked that how your mechanism cycle is happened like that. Unfortunately, I cannot answer. Really, it is going this cycle. That's why I told it is a proposed. Actually, this is a proposed mechanism. I'm not sure. Really, it is a rhodium hydrate is forming or something else is forming, and we try to analyze after the rhodium hydrogen complex. I'm sorry, Shankar. This I cannot answer because I unfortunately we didn't perform actually.
Okay, fine.
Yeah.
So because so this catalytic cycle is a very traditional cycle. What you have proposed,
Yes.
And
Exactly.
right, so
yes, exactly.
Yeah.
Actually, we also we discussed that several times with my PhD boss and their organometallics people, and we showed the some of the data, and they suggested even catalytic cycle is like a traditional cycle. I don't reaction is going very different manner like that. They suggested to us, and we also written same thing, and the reviewer also accepted.
Yeah, actually, the reaction what you have done it at plus 40 degrees Celsius, right?
Yes, 40 degree. Yes.
So even at low temperature, you are not able to trace anything.
No. Yes, low temperature. Actually, we didn't do the reaction at low temperature monitoring. We didn't do that. Maybe we can do. I think we can get it. I'm not sure that also. I'm not sure. Yeah, we didn't do. I'm sorry, Shankar. We didn't do.
Okay, fine. Thank you. So then it's very simple and direct question.
Yeah.
So you have made 6 different ligands.
Yes.
And then you have made 6 different rhodium catalysts. And
yes.
And 4 different iridium catalysts. Okay, among these catalysts, so which one is the best catalyst, and how do you justify?
Yeah, actually, what I will feel which is the best. Once actually we perform the reactions, then only we understood this reaction, this catalyst is the best. But in overall, I cannot say this reaction is the best for all reactions like that. I'm unable to say that. But whatever I showed, the first part of reaction, that the isopropyl and the mesitylene one, whatever is the substitution, that catalyst is the best for only hydrosilylation reaction. if we can use for other reaction, maybe other catalyst will be best.
Okay, so for this particular
Reaction, yes,
so isopropyl.
yes, that is the best. Yes.
Okay.
And also when I talk with the direct hydrogenation reaction, apart from B, all three catalysts show same ability. I think you can see you can observe same enantiomeric excess and all here. Sorry. See here. See, actually here 0 degree. See 88, 82, and 86. And here minus 20, see 87, 85, 85. These are these are the same. It's showing the same at 0 degree and minus 20.
Okay.
And actually, we cannot say this catalyst is best now in the regards, but we can do the several reactions. Then finally, only we can understand these reactions is universal for this. I think you know that story.
Yes.
Yeah.
Okay. So, okay, fine. So I'm done with that. So if any other questions are there, so you can.
Yeah. I'm happy to.
Yeah. So.
Yeah. Anybody have some inquiries, doubt, they can come and contact me directly. Also, they can ask me. No problem. I am very happy to answer. And everything I can answer it. They can send mail also. I will answer. Not a problem. Yeah, that's fine.
So thank you, Dr. Swami. So it's a very energetic talk and a lot of discussions and so many questions, and your answers were very prompt. Okay, so now I would like to call Ms. Parvati to say formal vote of thanks.
Okay.
Thank you, sir. I'd like to take this opportunity to thank our speaker, Dr. Chinnaya Swami, sir, for his wonderful and energetic presentation. Thanks to Shankar, sir, for chairing the session so successfully. Thanks to Sujit, sir, and the organizing team for successfully conducting back-to-back sessions of the webinar series. And it was a very interactive session, so special thanks to the audience for their active participation. Thank you.
Thank you all.
Yeah. Thank you everyone.
Thank you.
Yeah, I'm going log out.